So today we'll study pipelining concept further. All right. So what we have studied in the last class was a pipeline concept, and we have seen that in single cycle design, there is only one clock cycle available to us for doing all the operations. Okay, and that has its own limitation, right? Because when one stage is in operation, other stages remain unused. So throughput or overall instruction executed from the system or data path is just one instruction in one clock tick, which is too small, right? So better thing is that why not use parts which are unused with the concept of pipeline. But one thing we have seen that pipeline overall, pipeline design should be done in such a way that delay should be restricted. Okay, that's how end-to-end delay needs to be. That's because of combinational sequential logic circuits has to be restricted to something only. Then we can increase the clock speed. Whole idea is that we can increase the clock speed, and that can be done by reducing the maximum delay to the extent such that the work done can the maximum delay is less than clock tick, or work that is required to be done in that stage can be done in the clock cycle, right? So in order to do that, we put some registers in between. So for example, here we have put in a register, so this becomes one part, this becomes another part. Now these things, so basically whatever is here needs to be done within a clock cycle. So if this is not much, then we can increase the clock speed. That's the concept, right? And then we have seen the instruction, this this way of representation, which we are going to use in subsequent slides, right? So this is instruction memory when we write it with IM, and when we read instruction, uh, because instruction memory, anyway we are reading instruction, then we show this is in a kind of gray color or light blue color. I don't know what is shown in your slide set, but on the right hand side. So basically reading, when we are reading something from register file or instruction memory, is on the right side of that box. Okay, so register read is next. Then ALU is a fully colored symbol. Then we have data memory, where we have shown a small this data memory symbol. Okay, then register write. Note that register box here we are making it colored only on the left half. Okay, and there is a purpose for this kind of representation, right? Note that in the leading clock edge we do the writing, right? You note that, right? So if this is the one, okay, so we do writing here, so all right. And or maybe writing can be done here for previous phase, and then rest of the time this can be used. uh, okay, all right. And then whole instruction we show it using this kind of symbol. So if let's assume instruction fetch where the memory is involved, it takes 200 picosecond. Register is faster than memory, so let's assume that takes 100 picosecond. ALU takes 200 picosecond. For ALU operations, memory takes 200 picosecond and register takes 100 picoseconds. So overall 800 picoseconds. This work can be done. Okay, in case it's not pipeline. Okay, when we pipeline it in multi-cycle design, we see that it's like somebody in front of you in buffet queue takes more time than you are also stuck, right? So basically, overall, if we put this in a pipeline fashion, then the overall delay out of this 5-stage pipeline becomes overall 200 into this, a maximum time any stage can take, into 5. That's is equal to 1000 picosecond. All right. So it cannot be in single cycle design, this would have taken 800 picosecond approximately. All right. Okay. And then we have discussed in brief how we can do a pipelining of this kind, right? Okay, so this instruction in execution, when this is when this first instruction execution, and then when you execute second instruction, we can see that this is first clock tick, this is second clock tick, then second clock tick, second instruction starts, second instruction in fact is fetched in second clock tick. Third clock tick, we can see that the first instruction is in ALU operations are happening, in second instruction register read is happening, and so on, right? And this is third instruction. So at any point in time, if we have five stage pipeline, there can be five instruction. Okay, all right. So this is what we have seen in last class. This in case of single cycle, while this is in case of pipeline. So we can see that overall speed up, ideal speed up when all stages are balanced, will be same as number of stages. For example, in this case, had all instruction been taking all phases of the pipeline, or pipeline stages are taking say 200 milliseconds, then instruction would have taken will take about 2000 picosecond or milli 1000 picosecond, while in single instruction or single cycle design also take 1000 picosecond, but that's not the case. Here we can see it takes 800 picoseconds overall, while here what we can see is that in every 200 picosecond each instruction is executed when pipeline is full. Okay, so basically what we get here is speed up of 4 that we can see here. Okay, so this is how it happens, right? I mean, speed up is not same as number of stages in the pipeline, because some stages take more time than others, so speed up is less. So you can go through this, uh, how we achieve this very simple calculation, right? All right, so basically in single cycle each instruction is completed in 800 picosecond, while in case of pipeline design each instruction is completed in 200 picosecond. So ultimately what we speed up, what you get is 4 times speed. Okay, now let's see what exactly happens in pipeline. Okay, so initially pipeline is empty and then it gets becoming full. So this is the first instruction that we are executing is add T0, T1, T2. So T1, T2 contents are added and put into register T0. So this is instruction fetch, instruction decode and register fetch. Register values are fetched or register values are read, and then ALU operation. Now there is no memory operation here, and this is the last stage. Register write back. Result is addition of these two is written back here. This is the second instruction similarly, or T4, T3. So contents of register T4 and T3 are logically odd, and results are put into T3, and so on, right? So this is getting executed. Now we see what exactly is happening at each instant of time. So we can see that while instruction execution, each instruction, if you look, see the latency is still, latency is 1000 picosecond. Each instruction is taking 1000 picosecond, but lot of instructions are getting executed in parallel. Actually 5 instructions are getting executed in parallel, right? So we'll see this. So this kind of parallelism is called instruction level parallelism. Okay, or pipeline kind of parallelism is called instruction level parallelism. Okay, all right. So basically pipelining allows us to execute parts of multiple instruction at the same time using the same hardware. Okay, this is exactly what's happening. So what it says, execute parts of multiple instruction. So if you at the same time, right, using same hardware. Okay, so basically you can see time wise or you can see resource wise, right? So you can see that this resource ALU is being used by different instruction at different point in time. Okay, if you look at this way, then you can see at any point in time different parts of instructions, sorry, different parts of pipeline are being used by different instructions. All right. All right, so now let's see what's happening sequentially. Obviously this at each instruction level execution is happening sequentially, right? So these are all this happening sequentially. So these resources by an instruction over time. So this instruction, for example, is using these resources at different period of time, right? So this is in the one cycle, this second cycle, third cycle, fourth, fifth cycle, and so on, right? And we can see that at any point in time these resources are used in the pipeline by different instructions, right? So different parts of instructions are getting executed at one time slice, okay, or time slot. So here we can see the first instruction is using register file, is writing into register, while second instruction is doing nothing because this is memory is not. Third instruction is writing in is doing operations into ALU. Fourth instruction is using register file, is reading from register file, and the fifth instruction is reading from instruction memory. So at any time different parts of pipeline are being used, right? So effective utilization is more, and hence because of this throughput will be higher. So now let's come to design of data path. So this was the data path we have designed for single cycle. Now we need to modify this for modify this into pipeline design, right? Single cycle to pipeline. So this is a simplified design of this pipeline, right? The same thing we are representing as here. So there are 5 phases in this one: instruction fetch phase, decode and register read, execute, memory, and write back. Now we see that some are going to take more time. For example, data memory in our previous example was taking 200 picosecond. Similarly, memory, this was taking 200 picosecond. This was taking again 200 picosecond. Register was taking 100 picosecond. All right. So what we can do is that now it's very difficult to balance it, that each stage is going to take say 150 picosecond or 200 picosecond and so on. So but designers have done good job in fact of balancing, and it turns out that we'll have to put registers in between such that it's kind of this whole single cycle design gets splitted into pipeline design, right? So what we do is here that we put one set of registers here. So we need registers between stages. So one set of registers here such that now this can be completed in one clock cycle. And note that this clock cycle, the clock is higher speed and clock cycle time is less. This is the second one, second stage in pipeline. This third stage is the fourth stage. Now you can see this beauty of this, that so nicely done in RISC architecture, right? All right. So this is a same thing we are showing it here. So this now we have to put registers somewhere. So we'll put one set of registers here, second set of registers here, third set of registers here, and fourth set of registers at this place. Okay. Same thing. I mean, what we have discussed earlier, this is expanded view of that. All right. And now we actually put registers here. Okay. All right. Look at it carefully. You can see some changes. Say for example, we have put in one extra adder here. Note that we will doing PC plus 4 in single cycle design. We are taking it all the way up to this point, right? Okay. All right. So yes. See, if you see okay, single cycle design. If you see here, so PC plus 4 was going all the way up to, sorry, this point, right? Now the thinking is that why do we do that? Because it takes you let a, if you design chip in such a way that these two parts are, this header, and this thing is at two ends, then you'll have to carry this signal all the way uh, to the end, and that's not a good design, because it takes some time and so on. So what they have done is that instead of that, they have added one. They, anyway, we have to take the PC out, right? The same value of PC goes out. So for example, PC here comes here, the same value comes here in next cycle, and so on, right? Which is being used. So what it can be done is that we can add, put an adder here, and note that this PC value is being used at different places. Okay. Any other thing you notice? We do pipeline because number of instructions are have got to be in the flight. So different parts of the same pipeline should be used by different instructions. Okay, if you don't put registers, then signal will flow. As soon as you access second instruction, all this signal flow that we have seen in single cycle design will happen and cause problems. So we'll have to say that each phase of, or each part of the pipeline has to execute different instructions. That's the reason we have to separate this out. It's kind of separator. Okay, and as a result of that, of course, advantage is that clock cycle time is reduced, because all you have to take care of is just single stage in that clock cycle.
Okay, sir.
All right. So now the question I may ask you is that if there is a control unit here, and you say that as soon as instruction is fetched, and you also get some data from here, you generate control signals. All these control signals that you have seen, right? Now you generate these signals here when first instruction is getting executed, or instruction is fetched and then it comes to this place. But these are used in different clock ticks, right? These are getting used in all these clock, this whatever, for example, we are writing it back, then is in the fifth stage, corresponding thing should be here. Okay, that has to be used. Okay, so now what can be done? We'll have to see that. Okay, before that, let's take this example. This shows that a sequence of instruction, right? And each stage is actually executing different instructions. Take previous example and then you can see. Okay, all right. Here, for example, each instruction is part of the instruction is getting executed in different stages. The same thing is shown here. Okay, all right. This was the first instruction which is in execution, the second instruction, third instruction, fourth instruction, fifth instruction, in that sequence. This was the first, means that it's here, second, third, fourth, fifth. All right. So pipeline registers, pipeline registers separate stages, fine. The idea is that we'll have to separate the stages, otherwise signals will continue to flow. Hold the data for each instruction in flight. All right. Okay, so this was the question I have asked you, that you generate signal right in the beginning after it's fetched, instruction is fetched. This is a control unit that we have shown earlier at the bottom side of the diagram. And then you also let this flow. You store them. So there is a separate buffer you use to store these control signals and let them flow along the pipeline as they are needed. Okay, so like write back signal is going here, is going up to the last stage. Okay, any question?
Sir, so basically we are introducing some kind of memory to control unit.
Absolutely. Otherwise, control signals are generated right in the beginning when instruction is just fetched. It all lost. It's lost, right? Then second instruction will come. It will generate, is fetched, and then control signals are generated. Then those will be valid. So we have to then use this control signal until instruction is execution is over. First instruction until its execution is over, we need control signals, right? Otherwise, operations cannot be performed. And then we have to just buffer them, and then you propagate them as they are needed in later stages. That design can easily be done. Is in RISC architecture is beautifully done. It's very simple. Okay. Okay. So there is a trivia which says it's basically very simple. It says that if you remove load and stores from our instruction set, okay, and consider going from single cycle implementation 4-stage pipeline, then what will happen? What is going to be speed up and what is going to be latency? If this fetch is going to 200 picosecond, read is 100 picoseconds, and so on, as we have discussed earlier. Okay, so answer is very simple, that if we remove this memory access part, okay, there is no memory access, then we have instruction fetch, instruction decode, execute, and write back. So it takes 600 picosecond. So pipeline, basically pipeline. Now here, even now there is a misbalance because of ALU operation is going to take 200 picosecond and register read is taking 100 picosecond. So single cycle is taking 200 picosecond. While now each instruction, because of this 200 picosecond, when pipeline is full, will come out at 200 picosecond. So speed up is 3x. It's so that's the answer. And similarly, we can see that total latency means that how much each instruction is going to take time is now 600 picosecond, which is simple. And so now this is checking what is the difference in latency because of the pipeline. Okay, so now latency in case of pipeline for individual instruction will go up, okay, which is 800 picosecond, because 200 is maximum time any stage is taking. So and then each stage is has to take 200 picosecond. Okay, although register is able to finish the job in 100 picosecond, the wait time is still 200 picosecond. So overall, we can see latency or slowdown at each individual level is 1.33 times. Okay. So 1.33 times is slower in case of pipeline for an individual instruction. Okay, this is simple. Now, like we come to real life, that what we have discussed is a very simple thing. It's like food buffet, or in wedding you go and then buffet, and then each thing takes same time, and then queues moves simply, right? I mean, without any hassle, right? So life is not as simple in instructions, actual processor pipelines, and there are a lot of hazards, and like corona hazard that we are facing. I mean, life would have been smooth, normal, but these hazards keep coming in life, and somehow we have to manage them. Okay. So kind of hazards that we can see is three hazards, three main type of hazard. First is structural hazard. Okay. So basically, hazard is a situation that prevents starting the next instruction on clock cycle. In the next clock cycle means that the next instruction has to wait or do something, because certain things are it's like normal execution is not possible, and it's because of three hazards. First is structural hazard. Okay, so if the resource is busy, if one resource, for example, is used by one instruction, is also needed by next instruction. Now, what are the resources we have in pipeline? We can see by starting from left hand to right hand. We have instruction memory, program counter, instruction memory, and register file, then memory, and so on, right? Or ALU and memory, right? So if while these sequence of instructions are there, and it could be any sequence, then if the resource is being used by one instruction and also demanded by next instruction, then there is a hazard. Okay, structural hazard. So because of structure. Data hazard is that there's a data dependency between instructions. So we have to, in that case, next instruction has to wait until previous completes. Okay. And then third is control hazard, where flow of execution depends on previous instruction. So we'll see each one of these. Okay. In this class, we'll look only into structural hazard, and then next two classes will go into data hazard and control hazard. So now we are doing structural hazard. So structural hazard is happens when two or more instruction pipeline compete for access to a single physical resource. Okay, can you see this scenario in this pipeline? Can it happen? Okay, all right. So we'll see. And in general, to avoid this, when suppose a resource, say for example, any resource, say R1, uh, is used by instruction say I1, and at the same time instruction I2 wants to use this. Okay, now question is that if you design, if your instructions are so designed, right, or they are not uniform, they are complex kind, then this situation can easily happen. Okay, and if that is so, then one thing can be done is that this resource can be duplicated such that I1 uses first one and I2 uses second one. That's one way, right? So use okay, extra resources, which is second solution. And second of solution, another solution is that while this is being used by instruction 1, let instruction 2 wait. Once I1 completes use of this, then I2 can use it. This is called stall. Okay, these are the two solutions of structural hazard. Okay, first is that you know add more resources. If the for example, something register file or something, not register file, maybe some other ALU, for example. ALU is being used by one instruction, a second instruction also need to do similar stuff. Then you can create a system wherein you can have two ALUs, or that operation that you are trying to do, you can add that hardware. And we have seen that in case of single cycle pipeline, that when we have added a comparator. Okay, while comparator operation can be also done by ALU, but we never wanted that. We have added separate because of same reason. All right. Okay. Any question?
Sir, is the hazard what we are talking about something like one add register instruction wants to use ALU, but say a load word instruction also wants the use the ALU for adding address plus immediate?
Yes, at the same time.
Okay, sir, but it is happening in different stages, right?
No, no. So basically, same resource. ALU is being asked by two instructions that are in flight. Okay. Now you cannot visualize this scenario because the fact of the matter is that we have studied only RISC architecture and it's very simple. Now you assume, and in fact structural hazards don't happen in RISC architectures. the one which you are studying. Okay, so now you see here this sequence of instruction: load, add, store, subtract, or. And you see that in load, okay, when you're loading it from memory to register, the last stage is write back stage, which is registers being used. Okay, and then we can see this fourth instruction in the same time cycle. These are different time cycles. Okay, different time ticks, we can say, or different clock period. So in this time period, we can see this register is also being used. This register file is also used for fetching the value of register for subtract instruction, right? Now what are we doing? We are writing here and we are reading something from here. Okay, if you design register file in such a way that only one operation can be performed at a time, either writing or reading, then this problem can happen. Okay, now in order to overcome this problem, what we do is that we design the register file in such a way that reading and writing can happen simultaneously. Okay, all right. So, and also we have a separate port for reading and writing. Had we had same set of ports for reading and writing, it means where that port is being multiplexed. Sometimes it's being used for data input is going there. Okay, and sometimes you're taking data out from there, right? Had we designed in such a way, then things would have been complicated. Or had we designed in such a way the address lines, address port is same, both for writing and reading, then things would have been different, and then we would have ended up in a structural hazard. Okay, so we can avoid this by intelligent design. That's what is shown here, right? And so for example here, same example if you take here, okay, we can avoid this by this design where instruction and okay, I'm sorry. I'm sorry, it's just a minute. Okay, okay, just one part is skipped, which is that, so this concept where register reading and writing can happen together or in the same cycle, okay, writing and reading is called double pumping. Okay, that slide is missing here. Okay, so this is called double pumping. Also, we avoid this hazard by designing register which can be read and written in the same cycle. Okay, all right, so this is what it is. Now let's look at into memory access. Now what we had discussed earlier was register writing. So now we have here, can you see some issue? Now memory is being used here and memory is also being used here. Okay, and now what we are doing it here, reading, and of course memory is instruction memory is used in each cycle, right? Here also it's instruction memory is being used here. So now let's look in the first one, right? Here we are load word, we are reading it from data memory and bringing the data into register file. So this, in this cycle data memory is being used. Okay, while in this cycle, same cycle, for this instruction memory is used. Okay, do you see any problem? We don't see any problem. Had we had a single memory which contains both data, which can be used both for data as well as for instruction, then we have ended up into structural hazard. Okay, so single memory module would have caused structural hazard. Hence we have separate instruction memory and data memory. Okay, any question? Okay, all right.
Sir, am I audible?
Yeah.
Uh, Sir, I had a doubt that instead of making two memories, can we have like some buffer register where the instruction can be stored until the like current instruction has run, and then the second instruction can be sent to the same memory?
Yeah, you can see, you can do some intelligent designs, but note that it's not one instruction after other you are reading, right? There can be, instruction sequence can also be different. Okay, depending on flow of the program. That's one reason. And secondly, why do you want to do that? Uh, how do you predict that next instruction will require memory? See,
Yeah.
variants are always possible, but they are going to they might introduce complexities. Yes, you can prefetch instructions. Okay, but prefetching has certain advantage, and we'll see prefetching as a technique later on. Superscalar architecture actually use prefetching. Okay, so prefetching can be done, but at the same time, if you wrongly prefetch, then things may be different. And also then you can say that I am going to make some guess depending on code whether next instruction will be fetched or some other instruction. So all these are the advanced techniques, but you are right, thinking in right direction. It's possible to prefetch instructions and use them. All right. uh, so now coming back to structural hazard, we are in risk architecture that we have studied so far. This pipeline, we are avoiding structural hazard. Okay, all right. And that's the reason you see that we are using in actual design, most of the processor, including Intel processor, uses two caches. Okay, one is instruction cache and second is data cache. Because from instruction cache, instruction can be taken, from data cache, data can be taken, and all the data that is being supplied to cache comes from a unified memory. Okay, so this is the way it is, that we have two caches in most of the process. Otherwise, if it's single cache, then we'll see this structural hazard. All right, so let's move ahead another few minutes and then we'll close. And caches we have will discuss in later when we study memory organization. So these are small and fast buffer memories, right? So that we have already discussed in brief. Okay, all right. So structural hazard summary. Structural hazard happens because conflict for use of resources in the pipeline. Okay, uh, so we can see that this hazard will happen if pipeline is there with single memory. Okay, for load and store and so on, right? So however, we create separate memory modules for instruction and data, so this hazard is avoided. Okay. All right, so that's the next point. So RISC V is beautifully designed to avoid structural hazards. So yeah, we don't have this kind of hazards, but you can check it for Intel processor whether such hazards exist or not. Okay, uh, it's a lot of these things we don't see because RISC is very simple, right? And then we have simply split, the single cycle design into 5 phases that we have been studying right from beginning, right? I mean, and so we have simply added buffers in between. And then because of buffer, overall delay in a stage is limited, so clock cycle speed can be higher. And second thing is that instruction can move sequentially. A different part of instruction can be executed in pipeline manner. Okay, all right. But at the same time, note that when we generate control signals for the first section, those control signals also need to be carried along till the end, until they are exhausted or used. All right. So let's summarize. We have discussed in the brief what pipelining is. Okay, in the last class and this class, idea of pipeline is that increases the throughput. Earlier, each instruction, single cycle design, was taking say 800 picosecond, as considering the example we have used. And now each instruction is available in the pipeline, or each instruction is executed every 200 picosecond. Okay, because each clock tick, one instruction execution is over. All right, so we have a speed up because of that. Okay, and now the question you may ask is that why not, instead of five stages, why not make it 10 or 20 and increase the clock speed? That question we have answered in the last class, that it's not possible often to do it neatly without adding complexities. And second thing is the clock speed cannot be increased to such a high level because of power and heating issues. Okay. So now the beauty of this is that each component data path is efficiently utilized, right? Only inefficiency is when there are some hazard, okay, which we'll see later, or in the beginning when pipeline is empty, when first instruction is getting into pipeline, then and so on, right? But otherwise, is most of the time, most of the stages are used. Hence, the throughput, overall number of instruction executed in a period of time is much higher than in case of single cycle design. However, designing pipeline data path is not straightforward just by putting register between stages, right? And this is because of several reasons, right? I mean, first thing is that there can be dependency between instruction, so we can have different kind of hazards. Okay, we can have control hazard, data hazard, or structural hazard. And second thing is obviously the control signals also need to be, which are generated in the beginning for the first instruction, needs to be uh, carried along. So they must be stored and moved forward as the instruction progresses. Okay. So instruction, third instruction may use a component in a stage at the same time. Okay, so there can be structural hazard because of pipelining. However, RISC-V avoids structured hazard. So in complex architectures, like in case of CISC architecture, structural hazards are there and they can be resolved by stalling the instruction. It means that wait for second instruction to get into next stage until previous instruction finishes use of that particular resource. Okay. And second thing is that, much needed thing is that use extra hardware if possible. All right. Okay. So that's all for today.